Imagine you have a bag that has 8 oranges and 8 bananas. What would be the mass of such a bag? Well, assuming that the mass of the bag itself is negligible, the mass of such a bag would be the mass of 8 oranges plus the mass of 8 bananas, right? Seems pretty logical. Now that logic works well in simpler cases that we face in day-to-day life, but that doesn't happen exactly in the case of atomic nuclei. Now let us have a look at an example of an atomic nucleus. So for example, let us take the example of an oxygen nucleus. An oxygen nucleus is nothing but 8 protons and 8 neutrons. So we would expect that the mass of an oxygen nucleus would be the mass of 8 neutrons plus the mass of 8 protons. So let us first of all just find the mass of 8 neutrons and 8 protons and add them up. So the mass of a single neutron is, well, 1.00866 AMU. So we can just multiply that with 8 to get the mass of 8 neutrons, and the mass of one single proton is 1.00727 atomic mass units. So we can again multiply that with 8 because we have 8 protons, and that would give us the mass of 8 protons. So let me just calculate all that. So I get these values 8.06928 and 8.05816. Yeah, and I can now add these two values together. So this thing here, right here, is the mass of all the 8 neutrons, whereas this number right here is the mass of all the protons, obviously in atomic mass units. So if I add the mass of all the neutrons and the mass of all the protons, I should get the mass of the nucleus, right? Let me try that. So here I add both of them together. So 16.12744 AMU is the expected mass of an oxygen nucleus. Now, using mass spectroscopy and other such methods, scientists have found the mass of an oxygen nucleus to a very precise value, and the value of an oxygen nucleus that has been experimentally calculated turns out to be this 15.99053. And now that leads to a very weird thing. We expect the mass of an oxygen nucleus to be 16.12744, whereas the actual one is pretty different, and the difference between the two is substantial. And obviously some of you might expect this to be an experimental error or an error on our part while calculating the mass, but that is not so. Both these values are very accurate and their values are exact. I mean, there is no experimental error in this. So now how can this happen? There is a difference of, well, 0.13691 atomic mass units. So this number right here is kind of a defect in the calculations, or a defect in the mass somehow, because we expect the mass to be this, but it turns out to be this. So this is a defect in the mass, and well, that is what pretty much scientists call it. This value right here is called the mass defect, because this is kind of the difference between the actual value of the atomic of an oxygen nucleus and the expected value of an of an oxygen nucleus. And this is not only true for oxygen nucleus, but it is true for all the nuclei, and there is some difference between the expected and the actual value. And now let us actually understand why this difference occurs between the expected and the actual value, and where does this mass go. To understand why the mass defect occurs, I have a very decent analogy here. It's not a very perfect analogy, but I think this should make things clear to you. Here I have a few blades of grass, and obviously right now they are all scattered around. So obviously I want them to be together. I want to bind them together in one single bundle. So how do I do that? So right now I have, let's say, 1 2 3 4 5 6 7 8 9 10 11 12, around 12 blades of grass. Now how do I bind them together into one single bundle? Well, the simplest way to do is I can take 1 or 2 blades of grass out of them, take the rest of them, put them like this, and I can take that one single blade of grass, or that the one I had taken out, I can use that as a rope, or use that as something that I can tie all these blades of grass together. So there you go. I have used that one single blade of grass to tie all the other blades of grass, or rather bind them together in one bundle. So in this process, I have lost a single blade of grass, but I have been able to bind all the rest of the blades of grass together. Now, how is this example related to the example of an atomic nucleus? Well, you can consider all these blades of grass like the nucleons in a nucleus. So these are protons and neutrons, all of them scattered all around, and if I have to bind them all together, so obviously this is very different from the example of a nucleus, but if I have to bind all the nucleons in a nucleus together, so because the nucleons include protons, which are positively charged particles, they would obviously repel each other. So I need some energy, I need some force that can bind them together. So I need some energy to bind them all together. And where do I get that energy from? Well, in this example, I had taken one blade of grass and used that blade of grass to bind all of this grass together. So before binding, I had around 12 blades of grass, but now if I count, I am left with only 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 blades of grass. So now the blades of grass have reduced, and if I have to find the mass of grass that I have now, obviously I will not count the one being used to tie it, because that is not useless. So now the mass of the bundle of grass would be less, because I have used one blade to actually tie it all together. So if I now find the mass of the usable grass that I have, that will be less, or the mass of this bundle right here, that would be less than the total mass of all the blades. Why? Because I have used one of those blades to actually tie it all together. I have used that one blade to actually bind it together. Similarly, in an atomic nucleus, I take some of that. So when all those nucleons have to come together to form one nucleus, to bind it all together, we need some energy. Where do we get that energy from? Well, we take some of that mass from all those nucleons, that turns into energy, which then binds all those nucleons together into one giant nucleus, not a giant one, sorry, into one nucleus. And that energy that is required to bind them all together would obviously be called, you guessed it right, binding energy, because it is the energy required to bind all those together, just like we are binding grass here. Not a very good analogy, but anyway, binding energy. And where do I get that energy from? Well, I am taking some mass out of those nucleons, turn it into energy. How do I turn mass into energy? Well, we have Einstein's mass energy equivalence formula, which tells me that I can convert mass into energy if I multiply that mass with the square of the speed of light. Now, speed of light is a very giant number. Speed of light squared is a very, very giant number, and therefore even if I have a small amount of mass, so even if I take small amount of mass, which in that case was a mass defect, I hope you can now connect the dots, which was, that was a very small amount of mass. It was how much? 0.13691 atomic mass units. That is a very small amount of mass. But when that small amount of mass gets multiplied with the speed of light squared, such a large constant, I get a large amount of energy, which is the energy that is required to bind the whole all those nucleons together into one nucleus, and that is the binding energy. And so that is where that small mass goes, and that is the reason why the mass of a nucleus is slightly less than the mass of the individual nucleons that make up that particular nucleus. And if I have to now again take that particular nucleus and break it apart into all those individual constituent nucleons, I need to supply it that particular amount of binding energy, so that I can break it apart into nucleons. The amount of energy required to bind those nucleons together is equal to the mass defect, which is the mass, that mass that just vanishes, times the speed of light squared, and that mass that just vanishes while all those nucleons come together to form a nucleus, that mass defect, or the mass that vanishes, turns into binding energy that binds the nucleons together into one solid nucleus.